So we are going to work now, somehow we're going to connect to the last subjects treated by Anna before. We're going to speak about the integration of microalgae in a sustainable agriculture. That means where, when, and how we can push to the cultivation of algae. You have heard in these days everything about algae. You know that they are so nice, so they are autotrophic, but they can also be mixotrophic or heterotrophic. That means using organic carbon with light or without light. Of course, we know they need nutrients, so they can remove nutrients. They remove nutrients from the growth medium, and of course, if fed on wastewaters from wastewaters, and also in some cases, organic matter. They can produce valuable molecules and various kinds of compounds with important attractiveness, for instance, for the market of pharmaceuticals, of nutraceuticals, for cosmetic preparations, and so on. And concerning specifically agriculture, we know that they can act as natural pesticides and biostimulants for crops. However, their cultivation is not always economically sustainable, especially where the weather conditions are not optimal. That is the case of most European, Central and Northern European countries, if we make an exception for the Mediterranean countries. We have not always sunshine and adequate optimum temperature. So we have to push their productivity, and their cultivation can become convenient if the growth medium is inexpensive. That is the case of wastes, actually. And if the final valorization of biomass involves an economic income, and of course, if we can push productivity. Let's go directly to digestates. We know that biogas plants are a nice option to dispose of excess agro waste and animal sewage, also because we know that agricultural lands are not enough to receive all cattle sewage, cattle slurry, and so on. So we need to find a solution on the one hand, and we need to produce biogas as clean and renewable energy as you know. But more biogas means more digestates. And so actually we can apply soil, the solid fraction of digestate as amendment, but the liquid fraction must be treated, cannot be discharged as it is.
It is quite good because
what happens?
One of the panelists was unmuted. I took her. It's okay now.
So we need to treat the liquid fraction, and we can use it because in many cases it is a good substrate for algal growth. And we often speak about phytoremediation when using algae to remove nutrients from wastewaters. And we know that algae can grow on some liquid fractions of the digestate, but that the liquid fractions of the digestates are not all the same. They have quite variable properties according to the diet of the digestive. Literature is full of experience in this field, and as group we have also worked quite a lot. Here I will summarize shortly one of our experiences, and in this case we worked with the digestate from a piggery farm, and we worked for 200 days, so quite a long period, in Lombardy, so where, as I told before, the weather conditions are not so optimal for algae. We worked at pilot scale using a raceway with an area of about 4 square meters and a volume of about 1 cubic meter, mixed by a paddle wheel. To control pH, CO2 was bubbled, and this provided also an additional source of carbon just to push the growth of algae. And we had a quite concentrated liquid fed to algae, and algae grew without diluting the digestate. You see in the table, the concentrations were very high, and especially for ammonia nitrogen, we had concentrations which are much, much higher than the levels normally reported as toxic for microalgae. But in spite of this, algae could grow. We can see here the conditions, the temperature, and the irradiance, which were not so favorable. But anyway, we had a mixed population, and this is an important point. Mixed populations can grow also in non-optimal conditions. We had about 4-6 species defined by metagenomic analysis. You see them here, with a different succession of the dominance in the different periods. Anyway, they could grow. We had a productivity which is not excellent, but which is quite good for the conditions. We had 6.2 grams of total suspended solids per square meter per day as average. We removed completely ammonia nitrogen, and you saw that the value, the initial concentration was very high. But most of the initial ammonia nitrogen was nitrified, more than 60%, and about 7% was assimilated. Actually, the concentration of nitrogen in the algal biomass was 13%, which is quite comparable to the normally reported values. So what? We can produce algal biomass, but then we have to valorize it, and not all the possibilities are available for biomass grown on a dirty substrate as the digestates or the wastewaters in general. So a very interesting option we are working on now is the production of biostimulants. This could be a good way to close the loop. Speaking of circular economy, we can summarize things like that. We have agro wastes producing by anaerobic digestion, digestate and biomass. And we have the upgrading to biomethane, but as a consequence, the separation of CO2, which can be used by algae. So algae can be grown on the liquid fraction digestate, and CO2 can be added to microalgae to push their growth. From microalgal biomass, we can produce biostimulants, and in this way, we increase the production of crops. And again, we have agro wastes derived from both animal waste and crop wastes, which can go once more to anaerobic digest. The project working from now is this. I will try to summarize it shortly. We will integrate an algae cultivation in agricultural biomethane plants south of Milan, in the province of Cremona, to produce biostimulants, and how we want to go towards this goal. We will use agri-food biowaste, of course. We will use the liquid fraction digestate to provide nitrogen, phosphorus, and so on. And we will work on different steps. As you see here, first of all, the production of inoculum, then a phototrophic cultivation raceway, then heterotrophic growth to push the productivity. So what we will use is another waste. That means byproducts from a confectionery industry, which is quite close to the site of the future plant, the full-scale plant, and then harvesting, post-processing, and production of biostimulants. 2 points. We have told before that mixed consortia can grow quite easily and face also unfavorable conditions. But if we want to produce biostimulants to be sold, we need to have a quite constant quality. So we have to check that the culture is pure enough to ensure a quite reliable quality of the final biostimulant. So we have thought to produce a pure inoculum in a closed photobioreactor and to add part of this pure inoculum every day, about 10%, to the raceway in order to keep the dominance of the selected algal strain. The project will be located close to an industrial anaerobic digestion plant, as I told before, producing nearly 80,000 cubic meters per year of biomethane, and fed especially on cow slurry and cow manure and other agro-industrial byproducts. The plant produces by methane grading some 150 tons of CO2 per year, and this will be fed to algae. And it produces about 60 kilotons per year of digestate and about 50 kilotons per year of liquid digestate, of the liquid fraction of digestate, after separation via screw press. And this is another critical point, because the screw press is not so efficient in separation. So we have worked a lot to set up the most suitable way to produce a good liquid fraction to be fed to algae. Some basic assumptions here. The inoculum preparation will occur under controlled conditions, as I told before, and the raceway will be designed on the basis of the results of a model simulation, and of course on the basis of experimental results. Heterotrophic section is designed to triple the algal biomass density. That is our final goal. And that will work using confectionery waste, as I told you before. The biomass harvesting will be carried out by centrifugation after heterotrophic growth, without any further pre-concentration.
Valeria, 2 minutes.
I'm nearly finished.
Perfect. Thank you.
This is the scheme. This is the scheme of heterotrophic growth. And now we are working to validate the assumed parameters at pilot and lab scale about the critical points I indicated before. Till now, we have obtained some results. We have proceeded by a gradual acclimation of the algae to digestate, because at the beginning they didn't like it so much. So we started with 25% dilution, 40% dilution, concentration actually. And we are going on, first of all, at the lab scale, then at pilot scale, as you see here. We are working, we have worked monitoring the usual relevant parameters and considering the different possibilities to treat digestate in order to obtain a more suitable liquid for algae. And we have selected the suitable algal strains for the production of biostimulants. Now, some work is still in progress to test the biostimulant activity of the algal biomass. And we are going on, given we are obtaining quite encouraging results. The purity of algal biomass has always been over 95% with the system I described before. The photosynthetic efficiency of the algal culture has always been good. And ammonia was removed by assimilation and partial nitrification, but at the moment with a significant accumulation of nitrate, which, however, doesn't seem to be a problem in the case we use the effluent from the algal culture for fertirrigation. We have never had problems of bacterial contamination, and we have got carbon, nitrogen, and phosphorus concentration in the biomass in comparable to what we expected on the basis of previous experiences. So thank you for your attention. Thank you to all our collaborators, and